What if I told you that just 4 light-years from Earth, something massive is hiding in the darkness, sometimes appearing, sometimes vanishing, and challenging everything we thought we knew about our place in the universe? The James Webb Space Telescope is uncovering secrets that are rewriting the story of creation itself. Black holes that grow faster than physics should allow, planets that shouldn't exist, and worlds so close we could reach them within a single human lifetime. From dying stars on the brink of explosion to frozen planets wandering alone through the void, we're about to journey into the unknown. If you're fascinated by the mysteries of the cosmos and want to stay on the cutting edge of discovery, make sure to hit that subscribe button and turn on notifications. Your support helps us bring you the latest wonders from the universe. And trust me, you won't want to miss what's coming next. Let's dive in. Just 4 light-years from our planet, something enormous lurks in the closest star system to our own, and it has a habit of vanishing from sight. The James Webb Space Telescope has recently uncovered findings that are forcing us to rethink much of what we believed about the cosmos. There are black holes that have grown at impossible rates, planets that defy our understanding of how worlds form, and alien realms so near to us that, with the right technology, we could reach them within a human lifetime. Our journey will take us from stars on the brink of destruction to icy planets drifting alone in the darkness. If you find this fascinating, your support means more than you know. Take a deep breath. Let's begin. The distance between us and Alpha Centauri, the nearest star system, is just 4 light-years. If you could travel at the speed of light, you'd arrive before most people finish their university studies. In the grand scale of the universe, Alpha Centauri is right next door. In August 2024, the James Webb Space Telescope turned its golden mirrors toward this system and detected something no one had anticipated: a gas giant, similar in mass to Saturn, orbiting Alpha Centauri A at a distance about twice that between Earth and the Sun. This places the planet in what astronomers call the habitable zone, where conditions might allow for liquid water. While a gas giant itself isn't likely to support life as we know it, any moons orbiting such a planet could be promising. Think of the fictional moon Pandora from the movie Avatar, set in this very star system. Now, reality might be catching up to fiction, but things quickly became puzzling. When astronomers checked again in February 2025, the planet had disappeared. They looked once more in April, but it was still missing. It was as if the world had simply blinked out of existence. Scientists ran countless computer models to explain this oddity, and the answer they found sent a chill through the research community. The planet hadn't vanished, it had shifted position. Its orbit isn't a neat circle like Earth's, but rather stretched out, or elliptical. Sometimes, the planet swings so close to its star that the glare makes it invisible to Webb's instruments. At other times, it drifts farther out, becoming visible again. This means the planet is real, confirmed by multiple observations and supported by years of data from ground-based telescopes going back to 2019. If this discovery is verified, it would be the closest exoplanet ever directly imaged, a neighboring world seen with our own technology. And it's in a place we could, in theory, reach within a century using technology that's already being developed. But this finding raises difficult questions. Alpha Centauri is a binary system, with 2 massive stars locked in a gravitational dance, orbiting each other every 80 years. For a planet to survive in such a chaotic environment seems almost impossible. The gravitational forces should have torn it apart or flung it into deep space long ago. Yet, there it is, or was, waiting for us to notice. The research team is already planning more observations. They expect the planet to reappear when its orbit brings it back into view. The Nancy Grace Roman Space Telescope, set to launch in 2027, may finally confirm what Webb has hinted at: a world next door, hiding in plain sight, dancing on the edge of visibility. And if one planet can survive in such a turbulent system, what else might be hiding in the spaces between those twin stars? The answer may come sooner than we expect. But before we look further out, we need to look closer to home, because Webb also turned its gaze towards something heading straight for us. On December 27, 2024, astronomers spotted a rock tumbling through space. They named it 2024 WIRE4, and within weeks, it had the attention of every space agency on Earth. The asteroid measured somewhere between 130 and 300 feet across, about the size of a 15-story building. That might sound small compared to the asteroid that wiped out the dinosaurs. But an object this size hitting a city would unleash energy equivalent to several nuclear bombs. It would flatten buildings, incinerate everything nearby, and send shockwaves across an entire region. The real problem was its path. Early calculations showed a small but real chance that this asteroid could hit Earth on December 22, 2032. The odds started low, but then they rose. At one point, the probability of impact reached nearly 3%. That might not sound like much, but in the world of planetary defense, 3% is alarming. NASA made a decision that showed just how seriously they took the threat. They pointed the James Webb Space Telescope at the asteroid. This was extraordinary. Webb was built to peer into the distant universe, to study galaxies billions of light years away. Its time is precious and scheduled years in advance. Yet, they redirected it to track a tumbling rock in our own solar neighborhood. Why? Because Webb sees in infrared. It detects heat. That heat allows scientists to measure an asteroid's true size in ways that visible light cannot. When an asteroid reflects sunlight, its brightness depends on both its size and how reflective its surface is. A small, shiny asteroid can look just as bright as a large, dark one. This uncertainty made early estimates difficult. Was this rock 130 feet across and highly reflective, or 300 feet across and covered in dark material? The difference is huge when calculating potential damage. Webb's observations in March 2025 provided answers. The asteroid is about 160 feet wide, still large enough to cause regional devastation, but smaller than the worst-case scenarios. More importantly, continued tracking refined its orbit. By late February, NASA announced that the risk of impact had dropped to nearly zero. The rock would miss us. But the episode revealed something unsettling. We almost missed it entirely. The asteroid was discovered less than 8 years before its possible impact. If its path had been slightly different, or if the odds had been higher, 8 years might not have been enough time to mount a deflection mission. And here's what keeps planetary defense experts up at night. There are millions of asteroids in orbits that cross Earth's path. We've cataloged only a fraction of them. The next one might not give us 8 years of warning. It might give us 8 months or 8 days. Webb proved it can help, but it can't watch the whole sky. Something else is out there, something we haven't found yet. While we worry about the possibility of rocks falling from the sky, the James Webb Space Telescope has also revealed something even more unsettling about planets we once thought might be homes for life. About 40 light-years from Earth, a faint red star glows steadily in the darkness. This star, known as JWST, is orbited by 7 rocky planets, each roughly the size of our own world. When astronomers first discovered this system in 2017, it sparked imaginations everywhere. Here was a solar system with 7 Earth-sized planets, 3 of which sit in the so-called habitable zone, where liquid water could, in theory, exist. For the first time, humanity had found a place that looked like it might, just might, offer the right conditions for life. But when Webb took a closer look, the dream began to unravel. The innermost planet, TRAPPIST-1b, was the first to disappoint. By measuring its temperature as it passed behind its star and remerged, Webb found a scorched, airless surface, no atmosphere, just bare rock baking under relentless radiation. Next came TRAPPIST-1t, and the result was the same: no thick atmosphere, no protective blanket of gases, just another dead world. Then came the biggest blow, TRAPPIST-1d, which sits right on the edge of the habitable zone, had been the focus of enormous hope. It receives about as much energy from its star as Earth does from the Sun. If any planet in the system could support liquid water, this was the one. But in August 2025, researchers published their findings. Webb's instruments found no sign of water vapor, methane, or carbon dioxide, none of the molecules that make up a breathable atmosphere. The data pointed to 3 possibilities. Either the planet has an atmosphere, so thin it's like Mars, or it's wrapped in clouds so thick they block all detection, or it's simply a barren rock with no air at all. The lead scientist put it bluntly: TRAPPIST-1d is no longer a candidate for an Earth twin. Another hope extinguished. The culprit is the star itself. Red dwarfs like TRAPPIST-1 are volatile and violent. They unleash flares of radiation that dwarf anything our sun produces. These flares bombard nearby planets with enough energy to strip away atmospheres over millions of years. The planets in this system orbit so close to their star that a year lasts only a few Earth days. They are trapped in the blast zone of a stellar furnace. But not all hope is lost. The outer planets, TRAPPIST-1, F, G, and H, sit farther from the star and may have held onto their atmospheres. Webb is still watching, still searching. 15 more observations are scheduled for TRAPPIST-1 alone. Early hints suggest this world might have a nitrogen-rich atmosphere with traces of methane, similar to Titan, Saturn's largest moon. But the data isn't conclusive yet. The star's violent outbursts contaminate the readings, making it hard to separate planetary signals from stellar noise. We are pushing the limits of what any telescope can do. While we struggle to find signs of life on distant worlds, Webb has uncovered something even more puzzling about the early universe. Black holes that shouldn't exist. The universe is about 13.8 billion years old. In its earliest moments, there was nothing but hot plasma and radiation, no stars, no galaxies, no structure at all. Just a seething ocean of particles expanding outward from the Big Bang. Then gravity began its slow work. Matter clumped together. The first stars ignited. Galaxies started to form. And at the hearts of those galaxies, black holes grew slowly, feeding on gas and dust over billions of years until they became the supermassive monsters we see today. At least, that's what the models predicted. Webb has shattered those predictions. In November 2025, astronomers announced the discovery of a supermassive black hole in a galaxy called Cunningsess LRDZ86. The name is technical, but what it represents is staggering. This galaxy existed just 570 million years after the Big Bang. The universe was barely 4% of its current age, a cosmic infant. Yet at the center of this young galaxy, a black hole was already devouring matter at a rate that defies explanation. It was growing far faster than any model allows, far faster than physics says is possible. This is not speculation, it's confirmed, peer-reviewed, and published in Nature Communications. The black hole's mass compared to its host galaxy breaks every rule we thought we understood. In the modern universe, supermassive black holes typically contain about 1/10,000th of their galaxy's stellar mass. For every 10,000 units of mass in stars, there is roughly 1 unit of mass in the central black hole. This ancient monster, though, has a mass that's 10% of the galaxy's total, 1,000 times higher than the expected ratio. The research team described it simply: the black hole is growing faster than the galaxy that hosts it. But this isn't an isolated case. Webb has found hundreds of similar objects scattered across the early universe. Scientists call them little red dots because of their small size and reddish color in infrared images. Many of them appear to contain rapidly growing black holes surrounded by hot gas and dust. 70% of the little red dots examined so far show signs of active black hole feeding. Gas swirling at speeds exceeding 2 million miles per hour, temperatures hot enough to ionize atoms, energy output that rivals entire galaxies. These objects challenge everything we thought we knew about cosmic evolution. Either black holes in the early universe were born much larger than we assumed, collapsing directly from massive clouds of primordial gas, or they found ways to feed at rates that should be physically impossible. Or perhaps our models of the early universe are fundamentally flawed. The standard model of cosmology has guided science for decades. It has passed every test thrown at it, until now. Something happened in those first few 100 million years that we do not understand. Something that allowed monsters to grow in the darkness before the first light had fully dawned. And those monsters were not alone. Webb found something else lurking in the ancient cosmos galaxies that appeared too big, too bright, and too soon. When Webb first opened its eyes to the distant universe, astronomers expected to find small, dim, primitive galaxies. The early cosmos should have been a nursery of infant structures, tiny clumps of stars just beginning to form, building blocks that would eventually merge into the grand spirals and ellipticals we see today. Instead, they found giants, galaxies containing tens of billions of stars, fully formed, blazing with light, existing just 500 million years after the Big Bang. Some of them rivaled the mass of our own Milky Way, which took over 13 billion years to reach its current size. The headlines were immediate: universe breakers. These were objects so massive so early that they seemed to violate the fundamental laws of cosmic evolution. Scientists scrambled for explanations. The standard model of cosmology describes how the universe evolved from the Big Bang to the present day. It explains how matter clumped together under gravity, how dark matter formed invisible scaffolding for galaxies to grow upon, and how long these processes should take. According to this model, galaxies in the early universe should have been small. There simply wasn't enough time for them to grow large. Yet, there they were, massive and defiant. Some researchers began to wonder if the very foundation of our understanding was flawed. Maybe the properties of dark matter were different in the early universe. Maybe the constants of physics themselves had shifted over time. The implications were enormous. Decades of established science seemed to hang in the balance. But as more data poured in, a twist emerged. Many of these impossibly bright, massive galaxies were not what they first appeared. Their intense glow wasn't just from stars. Hidden at their centers were black holes in the act of feeding, devouring gas and dust at furious rates. The energy released by this process made the galaxies look far more massive than they actually were. When astronomers adjusted their calculations to account for these active galactic nuclei. The crisis eased. The number of truly massive galaxies in the early universe dropped, and the standard model of cosmology survived, battered, but not broken. Still, a mystery remained. Even after removing the black hole-powered imposters, Webb continued to see about twice as many large, early galaxies as theory predicted. Something about the conditions in the young universe allowed stars to form more quickly than they do today. Maybe the denser environment made it harder for stellar winds to blow gas away. Maybe the raw materials for star formation were simply more abundant. Or perhaps galaxies were just more efficient at turning gas into stars. In early 2025, Webb delivered another surprise: a massive spiral galaxy, nicknamed the Big Wheel, existing less than 2 billion years after the Big Bang. Spiral galaxies like this require stability and time to develop their graceful, rotating arms. Yet here was one, ancient and elegant, spinning in defiance of expectations. The early universe, it seemed, was not the chaotic mess we'd imagined. It was organized, structured, and mature in ways that challenged our assumptions. And while galaxies were taking shape, so too were worlds, some of them unlike anything we'd ever imagined. Picture a planet drifting through space with no star to orbit, no sunrise or sunset, just endless night in every direction. These are rogue planets, and Webb has revealed that they are far more common than anyone guessed. In 2023, the telescope discovered 42 pairs of these wandering giants in the Orion Nebula. Scientists called them Jupiter mass binary objects, pairs of gas giants orbiting each other, not a star, drifting together through interstellar space like cosmic dance partners with no stage. No one expected to find so many, and no one could explain how they formed. Then, in 2024, Webb looked even deeper. Astronomers pointed the telescope at a young star-forming region called NGC 1333, about 1,000 light-years from Earth. There, they found 6 more rogue planets, including the lightest ever detected, a world just 5 times the mass of Jupiter, surrounded by a disk of dust and gas. That disk changed everything. Dust disks are where planets form. Around normal stars, these disks condense into rocky worlds and gas giants over millions of years. But this rogue planet had its own disk. It could be forming its own miniature planetary system, moons, or perhaps something even stranger. Tiny worlds orbiting a frozen giant that itself orbits nothing. The discovery suggested that rogue planets don't just form around stars and get ejected. Some of them condense directly from clouds of gas, the same way stars do. They are failed stars, objects that gathered enough mass to collapse, but not enough to ignite nuclear fusion. And their numbers are staggering. Theoretical studies now suggest that rogue planets may outnumber the stars in our galaxy. For every point of light you see in the night sky, there could be several dark worlds drifting between them, invisible, silent, and cold. In 2025, astronomers detected one of these wanderers about 10,000 light-years away. They didn't see it directly, but instead watched as it bent the light of a distant star, a phenomenon called gravitational lensing. The rogue planet's mass warped space itself, acting like a cosmic magnifying glass. This world has about 70 times the mass of Earth, smaller than Saturn, larger than Neptune, and it drifts alone, unbound to any star. Confirmed through simultaneous observations from Earth and the Gaia Space Telescope. But perhaps the strangest discovery came when Webb and the Very Large Telescope observed a rogue planet called Char 7. This frozen giant is actively devouring gas and dust at a rate of 6 billion tons per second, accretion bursts that mirror the feeding behavior of young stars. Here was a planet acting like a star, growing and changing in the darkness. We don't fully understand what these objects are or what they might become. And while orphan worlds drift through the galaxy in silence, Webb has been watching something far more violent: stars preparing to die. For decades, astronomers have faced a puzzle. When massive stars reach the end of their lives, they explode as supernovae. The most common type of massive star is the red supergiant, bloated, aging giants that have exhausted the fuel in their cores. Theory says these stars should dominate the supernova population. But when scientists look at the records, red supergiants seem to rarely explode. Where were they hiding? On June 29, 2025, a supernova appeared in a galaxy 40 million light-years away. Astronomers named it SN25PHT. By tracing back through archived images, they made a discovery that solved a mystery stretching back generations. Webb had already photographed this galaxy in 2024. Hubble had observed it as far back as 1994. By comparing the images, scientists could identify the exact star that exploded. It was a red supergiant, confirmed at last. But here's why it had been invisible for so long. The star was wrapped in a cocoon of dust, so thick that it blocked almost all visible light. In optical wavelengths, it appeared more than 100 times dimmer than it should have. Hubble couldn't see it at all. Only Webb's infrared vision could pierce the veil and reveal the dying giant within. The star shone 100,000 times brighter than our sun, but the dust hid nearly all that light from view. This is the dustiest, reddest supergiant progenitor ever observed before explosion. It answers the question that plagued astronomers for years. The massive stars are exploding, but they're shrouded in cloaks of cosmic dust, invisible to telescopes that see only visible light. The lead researcher put it clearly. We've been arguing that dust might be hiding these stars. Even we didn't expect to see something this extreme. Webb caught the star in its final moments. The images show a bloated, unstable giant on the edge of collapse, and then the core gave way. Gravity won. The outer layers blasted outward at thousands of miles per second, leaving behind either a neutron star or a black hole. Hubble captured the aftermath in July 2025, a brilliant point of light where the hidden star once lurked. This discovery has far-reaching consequences. If the most massive stars in the universe are often hidden behind thick veils of dust, then our understanding of how often stars die in supernova explosions has been incomplete. The actual rate of these cosmic detonations might be higher than previously thought. That means the production of heavy elements, those forged in the intense heat of stellar death and scattered across the cosmos, could be more prolific than our calculations suggested. And there's another detail that hits close to home. The nearest red supergiant to Earth is Betelgeuse, a massive, unstable star in the constellation Orion, easily visible to the naked eye on winter nights. Betelgeuse has been dimming and brightening unpredictably. Some astronomers believe it could explode as a supernova within the next 100,000 years, or perhaps even sooner. When it does, it will shine so brightly that it will be visible during the day, a second star in our sky. But before we witness the death of a nearby giant, Webb has revealed something even stranger: a planet that shouldn't exist, shaped like a lemon and wrapped in an atmosphere that defies explanation. This bizarre world orbits a dead star at a distance of just 1 million miles. Compare that to Earth's 93 million miles from the Sun. A year on this planet lasts less than 8 hours, and the gravity is so intense that the planet has been stretched into an elongated, lemon-like shape. Scientists call it PSR JWST 322.265 but the technical name hardly matters. What matters is that this world breaks every rule of planetary formation. The host star is a pulsar, a neutron star, the collapsed core of a massive star that exploded long ago. Neutron stars are among the densest objects in the universe. A teaspoon of their material would weigh billions of tons. This one spins rapidly, completing thousands of rotations every second, sweeping beams of radiation across space like a cosmic lighthouse. But here's the mystery. The pulsar emits mostly gamma rays and high-energy particles, which are invisible to Webb's infrared detectors. That means the telescope could observe the planet without being blinded by starlight, giving researchers a perfect, unobstructed view. What Webb saw was astonishing. The planet's atmosphere is dominated by helium and carbon, no hydrogen, no water vapor, none of the familiar gases found on Earth. Instead, the skies are filled with dark soot-like carbon clouds. Deep inside, under crushing pressure, that carbon may be crystallizing into diamonds. The lead scientist described it as a new type of planetary atmosphere, unlike anything seen before. The findings were published in the Astrophysical Journal Letters in December 2025. The mystery deepens when you consider how this world formed. Most planets coalesce from disks of gas and dust around young stars. But this planet orbits a stellar corpse. Did it survive the supernova that created the pulsar? Did it form afterward from the debris? Or did it wander in from elsewhere and get captured? None of the standard explanations fit. One theory suggests the planet is actually the stripped remnant of a companion star. Pulsars sometimes have partners, and over billions of years, the pulsar can siphon material from its companion, whittling it down to a fraction of its original mass. Perhaps this lemon-shaped world is what remains of a star that lost 99.9% of itself. But even that doesn't fully explain the carbon atmosphere. Nuclear processes don't produce pure carbon in the quantities observed. The researchers admit they may be looking at an entirely new class of object, something between a planet and a stellar remnant, something that doesn't fit any existing category. And somewhere else in the galaxy, Webb found another world that shouldn't exist, a planet so close to its star that its surface is an ocean of molten rock. This world, called TOI 561b, orbits its star at such a blistering pace that a year lasts only 11 hours. Temperatures on the surface soar above 3,000 degrees Fahrenheit. By all known principles, this planet should be a bare, airless rock, stripped of any atmosphere by the relentless radiation from its star. But in December 2025, Webb detected something extraordinary. An atmosphere thick enough to redistribute heat from the day side to the night side, substantial enough to register in the telescope's infrared instruments. This shouldn't be possible. Planets this close to their stars are bombarded by intense radiation. Stellar winds and ultraviolet light should have blown away any atmosphere long ago. Yet TOI 561b still has one. After more than 10 billion years of existence. The planet is ancient, one of the oldest rocky worlds ever discovered, formed when the universe was less than half its current age. Somehow, despite all that time baking under the glare of its star, it has held onto a blanket of gas. Researchers call it a lava ball wrapped in air. Confirmed by 37 hours of continuous observation with Webb's infrared spectrograph. The measurements showed a dayside temperature far cooler than expected for a bare rock. If the planet had no atmosphere, it should have reached nearly 5,000 degrees. Instead, Webb recorded about 3,000. The only explanation is that gases are absorbing and redistributing heat. But what kind of atmosphere could survive under such conditions? Scientists believe the answer lies in the magma itself. Molten rock releases gases, volatile compounds bubble up from the interior and escape into the sky. On Earth, Volcanic eruptions do the same thing, but on a much smaller scale. On this hellish world, the entire surface is a volcanic ocean. The atmosphere is being constantly replenished from below. The planet essentially breathes through its lava. This discovery has profound implications for the search for life. Astronomers have long assumed that planets too close to their stars cannot maintain atmospheres. They were considered dead zones, unworthy of study. But if a world can replenish its atmosphere through geological activity, then the habitable zone might be wider than we thought. Not that TOI 561b is habitable. Nothing could survive on a world where the ground itself is liquid fire, but the principle applies elsewhere. Rocky planets with active interiors might be able to cling to their atmospheres in environments we once dismissed as hopeless. The rules are shifting. And they shifted again when Webb turned its instruments toward distant black holes, not just feeding, not just growing, but colliding, merging, and sending ripples through the very fabric of space, time. The earliest black hole merger ever detected was waiting in the ancient darkness, just 740 million years after the Big Bang. The universe was still young, galaxies were still forming, and two supermassive black holes were spiraling toward each other, locked in a gravitational death dance that would shake the very structure of space itself. Webb caught them in the act. The discovery, announced in 2024, represents the most distant black hole merger ever observed. Two galaxies crashing together, two monsters at their cores, circling closer and closer, destined to become one. This cosmic collision was confirmed through detailed spectroscopic analysis, which allowed astronomers to separate the light signatures of each black hole. One of these black holes contains a mass about 50 million times greater than our Sun. The other is likely similar in size, though it's buried so deep in gas and dust that precise measurements are still challenging. Eventually, these two titans will merge into a single supermassive black hole, combining the mass of 100 million stars. When that happens, the event will unleash gravitational waves, ripples in the fabric of space, time, that travel outward at the speed of light. These waves are too low in frequency for current detectors like LIGO to pick up, but future space-based observatories, such as the LISA mission planned by the European Space Agency, will be able to sense such ancient mergers. The lead scientist on the project explained the significance. Their findings suggest that merging is a key way for black holes to grow rapidly, even in the earliest epochs of the universe. But the implications go further. The two galaxies involved in this merger are relatively small, comparable in mass to the Large Magellanic Cloud, a dwarf galaxy that orbits the Milky Way. Yet each one harbors a supermassive black hole larger than the one at the center of our own galaxy. This ratio is unexpected. In the modern universe, black holes are usually much smaller compared to their host galaxies. But in the early cosmos, the balance was different. Black holes dominated, growing first, while galaxies struggled to catch up. Together with other discoveries from Webb, these results show that massive black holes have been shaping the evolution of galaxies from the very beginning. The merger also reveals something about the violence of the early universe. Galaxies didn't form in isolation. They collided, merged, tore each other apart, and rebuilt from the wreckage. The supermassive black holes at their centers were not passive bystanders. They were active participants in this cosmic chaos. When the two black holes in this system finally merge, they will release more energy in gravitational waves than all the stars in both galaxies combined. It will be a silent explosion, rippling through the universe at the speed of light. We can't see gravitational waves directly, but we can infer their presence from their effects. Webb has given us the before. Picture two black holes, still separate, still spiraling toward their inevitable union. While black holes were colliding in the distant past, Webb also uncovered unsettling truths about the galaxies that formed around them. These early galaxies were messy, turbulent, and struggling to survive. The Milky Way is a graceful spiral, with stars orbiting the center in orderly paths, tracing elegant arms that sweep across 100,000 light-years of space. It took billions of years for our galaxy to settle into this structure, for the chaos of formation to calm into the cosmic pinwheel we see today. Webb looked back to a time before that calm existed. In 2025, astronomers used the telescope to study galaxies that existed between 400 and 600 million years after the Big Bang. They expected to find young systems still organizing themselves, but what they found was even more chaotic than anticipated. The galaxies were turbulent and violent. Gas clouds weren't rotating smoothly. Instead, they churned with chaotic motions, slamming into each other at speeds that disrupted any attempt at structure. Stars formed in bursts, not in steady streams. The gravitational forces within these galaxies pulled in every direction at once. One researcher described it simply: these early galaxies struggled to settle. The observations were made using a technique called grism spectroscopy, which allowed Webb to measure the motion of gas within individual galaxies. The data revealed velocity dispersions far higher than those seen in modern galaxies. Gas was moving erratically, driven by supernova explosions, black hole activity, and gravitational interactions with neighboring systems. This is the most detailed look yet at how galaxies formed, and the findings were published in the monthly notices of the Royal Astronomical Society. The results help explain something that had puzzled astronomers for years. Early galaxies often appear clumpy and irregular in Webb's images, with bright knots of star formation scattered across their surfaces and no clear pattern. Now we understand why. The gas from which those stars formed was itself disordered. Turbulence prevented the smooth, rotating structures that would come later. But there's a deeper implication. If galaxies in the early universe were this chaotic, then the environments for planet formation were equally hostile. Stars born in violent bursts may have scattered their planetary disks before worlds could fully form. Black holes feeding aggressively may have sterilized entire regions with radiation. The places where life could have arisen were rare, and yet some galaxies did manage to organize earlier than expected. The spiral galaxy nicknamed the Big Wheel, discovered in early 2025, shows elegant rotating structure despite existing less than 2 billion years after the Big Bang. Somehow, this galaxy avoided the worst of the chaos, or perhaps it found a way to calm itself faster than its neighbors. The early universe was not uniform. Some regions were violent, others were stable, and in those stable pockets, the conditions for complexity could emerge. Webb is helping us map which regions were which. But stability wasn't the only requirement for complexity. Planets also needed protection. And Webb revealed that around the most common stars in the galaxy, that protection may be impossible to maintain. Red dwarfs are everywhere. They make up about 70% of all stars in the Milky Way. Small, dim, and long-lived, they burn their fuel so slowly that they can shine for trillions of years. If life needs time to evolve, red dwarfs offer more time than any other type of star. But there's a problem: red dwarfs are violent. They unleash flares of radiation with frightening regularity, bursts of ultraviolet light and charged particles that dwarf anything our sun produces. These flares aren't rare, they happen constantly, especially in young red dwarfs, and the planets that orbit these stars sit dangerously close to the blast zone. Because red dwarfs are dim, their habitable zones are narrow and close. A planet needs to orbit within a few million miles to receive enough warmth for liquid water. At that distance, stellar flares become existential threats. Webb's observations of the TRAPPIST-1 system revealed this danger in stark detail. The 7 planets orbiting TRAPPIST-1 are bathed in radiation. The star is known to be volatile, releasing flares that have been recorded by multiple observatories over the years. These flares don't just warm the planets, they strip atmospheres away, molecule by molecule, over millions of years. The inner planets have already lost any protection they might have had. TRAPPIST-1b and c show no signs of substantial atmospheres. TRAPPIST-1d, once considered a prime candidate for habitability, appears similarly barren. The outer planets may have fared better simply because they sit farther from the worst of the radiation. But distance alone isn't enough. Even TRAPPIST-1, the most promising world in the system, faces an uncertain future. Researchers studying the planet found that the star's activity contaminates their atmospheric readings. Flares emit light at specific wavelengths that can mimic the signatures of planetary gases. Separating the star's signal from the planet's is extraordinarily difficult. 15 additional observations have been scheduled to account for this interference. Scientists will observe TRAPPIST-1 alongside the inner planet TRAPPIST-1b, which is believed to be a bare rock. By comparing the two, they can subtract the star's contribution and isolate any atmosphere on the outer world. If TRAPPIST-1 turns out to have no atmosphere, the consequences reach far beyond this single system. Red dwarfs are the most common stars in our galaxy, and if their planets can't hold onto their air, then the majority of potentially habitable worlds may actually be barren. The search for life would become much more difficult, narrowing the field dramatically. Still, the James Webb Space Telescope hasn't given up. It continues to monitor red dwarf systems, looking for exceptions, worlds that somehow survived the onslaught, planets that managed to keep their atmospheres against all odds. Each new observation is a test of our assumptions, a chance to find a rare survivor in a hostile environment. While some planets struggle to keep their air, others are forming in ways no one predicted. For decades, astronomers could only infer the existence of planets by indirect means, watching stars wobble under the gravitational pull of unseen companions, or measuring the tiny dips in brightness when a planet crossed in front of its star. Direct imaging of planets was a dream, reserved for the most massive worlds orbiting far from their stars. But in June 2025, Webb achieved something never done before. It directly imaged a planet in the process of forming, embedded within the debris disk of a young star. This star, known as JWST, is located about 111 light-years from Earth and is a cosmic infant only 6.4 million years old. It's still surrounded by rings of gas and dust left over from its birth. These rings are the raw material for planet formation. And for the first time, we have seen a planet in the act of assembling itself. The new world sits in a gap between the first and second ring of the debris disk, with a mass about 1/3 that of Jupiter. It orbits its star at a distance 52 times greater than Earth's distance from the Sun, a cold, distant world still gathering material from the surrounding dust. The odds of this being a background galaxy masquerading as a planet are less than 1%. The discovery is remarkable for several reasons. First, It validates a long-standing theory: gaps in debris disks are often caused by planets clearing out lanes as they orbit, like snowplows pushing through fresh powder. TWA7's disk has 3 distinct rings, suggesting there may be more planets waiting to be found. Second, this is a snapshot of planetary construction in progress. We're not looking at a finished world, but at a planet still embedded in the disk that birthed it, still accreting material, still evolving. Third, it demonstrates Webb's extraordinary precision. Directly imaging a planet requires blocking out the overwhelming glare of its parent star, and Webb's coronagraphs and image processing techniques made it possible to isolate this faint point of light from the stellar noise. The research team specifically targeted young stars that could be viewed from above, providing a clear view of the disk structure and any planets within it. TWA7 is just the beginning. Other young systems are already lined up for observation. The technique is proven, and the hunt for newborn worlds continues. There's something poetic about this discovery. We are watching a planet form around a star that is itself a baby by cosmic standards. Creation is unfolding in real time, the universe building new worlds even as we observe. But formation is only half the story. Webb has also captured the opposite end of existence, the farthest supernova ever seen, a star dying at the edge of the observable universe. About 730 million years after the Big Bang, the universe was just emerging from its dark ages. The first stars had ignited. The first galaxies were beginning to glow, and somewhere in that primordial light, a massive star collapsed. The explosion released more energy in seconds than our sun will produce in its entire 10 billion year lifetime. A gamma-ray burst shot outward at nearly the speed of light, and behind it, the expanding shell of the supernova carried heavy elements forged in the dying star's core: iron, nickel, cobalt, the building blocks of rocky worlds scattered into the void. 13 billion years later, Webb caught the afterglow. On March 14, 2025, a space telescope called SVOM detected a brilliant flash of gamma rays. Follow-up observations with the Very Large Telescope confirmed the distance. The light had traveled from an era when the universe was just 5% of its current age. Then Webb pointed its infrared eye at the source. Roughly 110 days after the initial burst, the telescope captured images that separated the fading supernova from its host galaxy. The explosion was still visible, still glowing, even after billions of years of travel across the expanding cosmos. This is the most distant supernova ever confirmed, and the discovery was published in Astronomy and Astrophysics in December 2025. This matters because it connects two phenomena that scientists have long believed are related. Gamma-ray bursts are among the most energetic events in the universe, but their exact origins were debated for decades. The leading theory was that long-duration gamma-ray bursts are produced by collapsing massive stars, supernovae. Webb provided the smoking gun. The supernova emerged at exactly the same location as the gamma-ray burst, in the same host galaxy. The massive star that created the burst also exploded as a supernova. Theory confirmed. But there's more. The host galaxy is small and faint, one of countless dwarf galaxies that populated the early universe. Inside that tiny system, a single massive star lived and died, seeding its surroundings with heavy elements that would eventually form new stars, new planets, and perhaps even life. We are connected to events like this one. Every atom of iron in your blood, every speck of calcium in your bones, was forged in a stellar explosion billions of years ago. The supernova Webb observed is part of that lineage, a distant ancestor in the cosmic family tree. And the telescope is still watching, still searching the ancient light for more explosions, more gamma-ray bursts, more evidence of the violent processes that shaped the universe we inhabit today. But the early universe held one more secret. Something even older than the first supernova, the echoes of the very first generation of stars, known as population Earth stars. These were the first-born, colossal giants forged from pure hydrogen and helium, the only elements that existed in the aftermath of the Big Bang. No carbon, no oxygen, no metals of any kind. Just the simplest atoms, collapsing under gravity until fusion ignited in their cores. Population Earth stars were massive beyond anything that exists today. Hundreds of times heavier than our Sun, they burned hot and bright, consuming their fuel in just a few million years before exploding and seeding the cosmos with the first heavy elements. Every atom heavier than helium that exists today traces its origin to these primordial giants. But no one has ever seen one directly. They died too long ago, their light stretched and dimmed by 13 billion years of cosmic expansion. Webb may have found their fingerprints. In 2024, astronomers studying the galaxy JWST discovered something unexpected in its outer halo. A cloud of gas with no heavy elements at all, pure hydrogen and helium, pristine material unchanged since the Big Bang. This cloud could be the birthplace of population Earth stars, the raw material from which the first generation would have formed. The discovery of this untouched gas cloud is not a direct sighting of a population Earth star, but it's the closest we've come to witnessing the dawn of stellar creation. Scientists are careful to point out that they haven't actually observed one of these primordial giants, but the presence of pristine hydrogen and helium in the outskirts of an ancient galaxy is exactly what theory predicts. The ingredients are there, the conditions are right, and JWST, one of the most distant galaxies ever observed, existing just 430 million years after the Big Bang, offers a rare glimpse into the universe's earliest days. At its center, a supermassive black hole is devouring matter at a ferocious rate, but on the edges, untouched pockets of primordial material still linger. This is as close as we've come to seeing the birthplaces of the first stars. The significance of this extends far beyond curiosity. Population Earth stars are believed to have produced the first black holes through direct collapse. They may have triggered the formation of the first galaxies by ionizing the surrounding gas, transforming the universe from a dark, featureless void into the structured cosmos we see today. If Webb can find more of these pristine gas clouds, scientists will be able to study the conditions under which the first stars formed, test models of primordial nucleosynthesis, and trace the chemical evolution of the universe from its simplest state to the complexity we observe now. The ghosts of the first light are still out there, hidden in the faintest signals from the most distant reaches of space. And Webb is listening. While the telescope peers into the ancient past, it has also revealed something troubling about the present. And the universe is expanding, and it's doing so faster than our best models predict. The idea that the universe is getting bigger isn't new. Edwin Hubble first measured the expansion in the 1920s, and since then, astronomers have refined the measurement countless times, trying to pin down the so-called Hubble constant, a number that describes how quickly the universe expands per unit of distance. The problem is, the numbers don't agree. When scientists measure the expansion using nearby stars and galaxies, they get one value, around 73 kilometers per second per megaparsec. But when they use the cosmic microwave background, the faint afterglow of the Big Bang, they get a different value, closer to 67. The difference is small, but it's far too large to be explained by measurement error. Something is off, either with the measurements or with our understanding of the universe itself. This discrepancy is known as the Hubble tension, and it has haunted cosmology for more than a decade. Webb was expected to help resolve it. In December 2024, researchers published the largest study of cosmic distances ever conducted with Webb. They used 3 different methods to measure distances to galaxies that hosted supernovae, cross-checking everything and combining data from multiple independent teams. The result was clear. The Hubble Space Telescope's measurements were accurate. The discrepancy wasn't caused by calibration errors or instrument problems. Webb confirmed what Hubble had been saying all along: the universe is expanding faster than the standard model predicts. This leaves 2 possibilities. Either there is some new physics at work, accelerating expansion in ways we don't yet understand, or the standard model of cosmology, which has guided science for decades, is incomplete. Dark energy is already part of the model, a mysterious force that drives galaxies apart faster and faster over time. But dark energy alone doesn't explain the Hubble tension. Some theorists suggest that dark energy might change over time, behaving differently in the early universe than it does today. Others propose new particles or forces that operated in the first few 100,000 years after the Big Bang. The possibilities are vast and unsettling. The discrepancy suggests that our understanding of the universe may be missing something fundamental. Adam Riess, the Nobel laureate who led the study, put it plainly: the evidence suggests that the expansion of the universe is accelerating faster than our models predict, and we don't know why. Webb hasn't solved the Hubble tension, it's made it more mysterious. The puzzle has only deepened, and mysteries seem to follow this telescope wherever it looks, including toward a red giant star that may soon give us the show of a lifetime. On a clear winter night, if you look up at the constellation Orion, you'll see a bright reddish star at the hunter's shoulder. That's Betelgeuse, one of the largest stars visible to the naked eye. If it were placed at the center of our solar system, its surface would extend past the orbit of Jupiter, maybe even Saturn. Betelgeuse is bloated, unstable, and nearing the end of its life. It will explode as a supernova, this is certain. The only question is when. In late 2019 and early 2020, Betelgeuse dimmed dramatically, fading to less than half its normal brightness. The world took notice. Was the star about to explode? Would we witness the death of a nearby giant in real time? The answer, it turned out, was no. The dimming was caused by a cloud of dust ejected from the star's surface, temporarily blocking its light. Betelgeuse wasn't dying, it was coughing. But the episode revealed just how unstable the star has become. Webb and other observatories have continued to monitor Betelgeuse, tracking its temperature, brightness, and the structure of its outer layers. The data shows a star in turmoil. Surface temperatures fluctuate, material is ejected into space, and the star pulsates, swelling and contracting over periods of months. Some researchers believe Webb has detected signs of accelerating instability, changes in the infrared signature that suggest the core may be approaching collapse. But predictions are difficult. In astronomical terms, imminent could mean tomorrow or 100,000 years from now. What we do know is that when Betelgeuse finally explodes, it will be spectacular. The supernova will outshine the full moon and be visible during the day, a brilliant point of light in the blue sky. For weeks, maybe months, humanity will watch a star die 56 light-years away. But we are safe. The distance is too great for the explosion to harm Earth. No deadly radiation will reach us, no shock wave will disrupt our atmosphere. We will simply witness one of the most powerful events in the universe from a front row seat. The heavy elements forged in that explosion will eventually drift through space, mixing with clouds of gas and dust, seeding future generations of stars and planets. Some of those elements may one day become part of new worlds or even new life. We are stardust, watching stardust prepare to scatter. And when it happens, Webb will be watching too, recording the death of a giant in unprecedented detail, adding another chapter to the story of how stars live and die. But the story doesn't end with death. It continues with creation. And Webb has found places where creation is happening right now, on worlds that orbit nothing at all. A planet without a star seems like a dead end, a frozen ball of gas or rock drifting through the void, cut off from the warmth and energy needed for anything to evolve. For a long time, astronomers assumed these so-called rogue planets were cosmic orphans, doomed to eternal darkness and inactivity. But the James Webb Space Telescope has upended that assumption. In July 2025, astronomers published findings that challenge everything we thought we knew about how planets form and what they can become. Using Webb's sensitive infrared instruments, researchers studied 8 rogue planets with masses between 5 and 10 times that of Jupiter. These giants float freely through space, unbound to any star. What they found was remarkable. 6 of these planets were surrounded by extended clouds of warm dust, the unmistakable signature of debris disks. These disks are similar to the swirling rings of gas and dust that surround young stars, the very structures from which planets, moons, and asteroids are born. But here the central object is not a star, but a planet. Even more intriguing, Webb detected silicate grains within these disks. Silicates are minerals, the building blocks of rocky worlds. Their presence means that dust is clumping together, beginning to crystallize, taking the first steps toward forming solid objects. In other words, these massive rogue planets may be nurseries for miniature planetary systems. They could be building moons, or perhaps something even stranger, tiny rocky bodies orbiting frozen giants that themselves orbit nothing at all. The implications are staggering. Planetary formation is not exclusive to stars. Lonely, starless worlds drifting through the galaxy can build their own companions. The lead researcher put it simply. The process of forming planetary systems might work around isolated planets, not just around stars. This discovery forces us to expand our definition of what a planetary system can be. We've always imagined planets orbiting stars. Now, we must imagine planets with their own satellites, systems within systems, all the way down. And there may be trillions of these objects in our galaxy alone. Rogue planets are notoriously difficult to detect. They emit almost no light, don't reflect the glow of a parent star, and don't transit across a stellar disk. They are invisible against the blackness of space, unless you know exactly where to look and have instruments sensitive enough to catch their faint heat. Webb can see them, and Webb is finding them everywhere. The 6 rogue planets with debris disks were discovered in a young star, forming region about 1,000 light-years from Earth. But similar objects likely exist throughout the galaxy, in the spaces between stars, in the halos of galaxies, in the vast emptiness that separates one stellar neighborhood from another. We have only begun to map this hidden population. If rogue planets can form moons, what else might they harbor? Could liquid water exist beneath the icy surfaces of their companions, warmed by tidal forces and radioactive decay? Could chemistry proceed in those dark oceans, sheltered from the harsh radiation of space. The questions multiply faster than the answers. But Webb's discoveries aren't limited to the distant reaches of the galaxy. The telescope has also found something much closer to home, a cold giant lurking in our own stellar neighborhood, captured in unprecedented detail. Just 12 light-years from Earth, a failed star drifts through the darkness. It's called Epsilon Indi Ab, and until recently, it was little more than a gravitational whisper, a subtle tug on its parent star that hinted at something massive nearby. Webb turned that whisper into a portrait. In 2024, astronomers used the telescope to directly image this object, confirming its existence and revealing its properties in detail never before possible. Epsilon Indi Ab is a gas giant roughly 6 times the mass of Jupiter. It orbits its star at a distance similar to Saturn's orbit around our Sun, and it is one of the coldest exoplanets ever directly observed. Surface temperatures hover around 200 degrees below 0 Fahrenheit, cold enough to freeze methane, cold enough to condense exotic ices that don't exist on any world in our solar system. The planet is real, visible, and studied. What makes this discovery significant isn't just the planet itself, but what it represents for the future of exoplanet science. Most exoplanets are detected indirectly. We see the wobble they induce in their stars, or the dimming they cause when they pass in front of a stellar disk. But direct imaging captures actual light from the planet itself, photons that traveled from that distant world to Webb's mirrors, giving us a real picture of an alien atmosphere. Epsilon Indi Ab is close enough and cold enough that Webb could study its composition. The data suggests an atmosphere rich in methane and possibly ammonia, similar in some ways to Jupiter and Saturn, but colder, older, and more evolved. The planet has been cooling for billions of years, slowly radiating away the heat of its formation into the emptiness of space. Epsilon Indi Ab orbits a star that is itself remarkable. Epsilon Indi A is a K-type star, slightly smaller and cooler than our Sun. It's part of a triple system that includes 2 brown dwarfs, failed stars that never ignited fusion in their cores. The planetary architecture of this system is complex. Multiple objects of varying masses, all bound together by gravity, all influencing each other's orbits over billions of years. By studying Epsilon Indi Ab, scientists can learn about planetary evolution in ways that observations of our own solar system cannot provide. Jupiter and Saturn are about 4.5 billion years old. Epsilon Indi Ab may be even older, representing a more advanced stage of giant planet aging. What happens to atmospheres over such timescales? How do clouds form and dissipate? How does internal heat escape through layers of exotic gas? Webb is beginning to answer these questions, and the answers will inform our understanding of giant planets everywhere, including those that might harbor moons with liquid water, moons where life could theoretically arise, even around cold, ancient worlds far from the warmth of any star. But warmth isn't always necessary. As Webb has shown, sometimes heat comes from unexpected places. When we think of habitable worlds, we picture Earth, a rocky planet bathed in starlight, warmed by a yellow sun, wrapped in a protective atmosphere. But habitability might take forms we never imagined. Deep inside frozen worlds, heat can persist for billions of years. That the source isn't starlight, but something more subtle, radioactive decay. The slow breakdown of unstable atoms buried in a planet's core releases energy, warming the interior from within. And tidal forces, the gravitational stretching and squeezing that occurs when a moon orbits close to a massive planet, generate friction, which in turn creates heat, enough heat, in some cases, to maintain liquid water beneath shells of ice. This isn't just theory. We see it in our own solar system. Europa, a moon of Jupiter, has a global ocean beneath its frozen crust. Enceladus, a moon of Saturn, shoots geysers of water vapor into space. Both worlds are heated not by sunlight, but by internal processes. Both are considered among the most promising places to search for life beyond Earth. The James Webb Space Telescope has observed these icy moons, measuring their surfaces, analyzing their chemical makeup, and searching for signs of geological activity. What Webb has found suggests that the conditions for subsurface oceans are not rare. In fact, they may be common throughout the galaxy. Rogue planets with large moons could harbor similar environments, frozen on the outside, but warm and wet beneath, cut off from starlight yet sustained by the slow burn of radioactive elements and the relentless pull of gravity. Life in such places would be alien in ways we can barely imagine. There would be no photosynthesis, no connection to a star's energy, just chemistry proceeding in darkness, powered by the planet's own internal heat. Scientists call this process chemosynthesis. On Earth, it occurs in the deepest ocean trenches, where hydrothermal vents spew mineral, rich water into the abyss. Entire ecosystems thrive there, independent of sunlight. Tube worms, blind shrimp, and bacteria that metabolize sulfur instead of oxygen. If such life can exist on Earth, it could exist elsewhere. Webb cannot detect life directly, no telescope can, but it can identify the conditions that make life possible: liquid water, chemical energy sources, and stable environments over geological timescales. The telescope has found these conditions in places we never expected: around rogue planets, inside debris disks, and on frozen moons orbiting distant giants. The search for life is no longer limited to the so-called habitable zones of stars. It now includes the dark spaces between them, the frozen wanderers, and the hidden oceans. The universe is larger and stranger than we ever imagined, and Webb is just getting started. But not all of its discoveries inspire wonder. Some are sobering reminders that our cosmic neighborhood is full of objects we have only begun to catalog. We have mapped the stars, charted the galaxies, and traced the structure of the cosmic web across billions of light years. Yet there is a population of objects that has largely escaped our survey's: brown dwarfs. These are failed stars, objects that formed from collapsing clouds of gas, just like stars do, but never gathered enough mass to ignite hydrogen fusion in their cores. They glow faintly with the residual heat of their formation, then slowly fade into darkness over billions of years. Webb has revealed that brown dwarfs are far more numerous and diverse than we realized. In December 2025, the telescope captured images of a young star cluster called Westerlund 2, located about 20,000 light-years from Earth. Hidden among the brilliant young stars, Webb found a population of brown dwarfs with masses as low as 10 times that of Jupiter. These are among the lightest free, floating objects ever detected through the process of stellar formation. They blur the line between planets and stars, too large to have formed in a planetary disk, too small to sustain fusion. Something in between. The cluster contains approximately 3,000 stars and an unknown number of these transitional objects. The discovery challenges our categories. What do we call an object that forms like a star but has the mass of a planet? Is it a failed star or a successful planet? The distinction matters because it affects how we count objects in the galaxy, estimate the total mass of matter, and model the evolution of stellar populations. Brown dwarfs are not the only hidden population. Webb has found objects even smaller. rogue planets with masses just a few times that of Jupiter, drifting through star-forming regions without any stellar companion. These objects may have been ejected from planetary systems or collapsed directly from gas clouds before they could grow larger. The galaxy is crowded with these invisible wanderers. Traditional surveys using visible light miss most of them. Brown dwarfs are too cool and faint, and rogue planets are even harder to detect. Only infrared telescopes like Webb can spot their dim thermal signatures against the cold background of space. The implications are significant. Dark matter is the invisible scaffolding that holds galaxies together, and its nature remains one of the greatest mysteries in physics. Some researchers have speculated that brown dwarfs and rogue planets might account for a portion of this missing mass. The numbers don't quite add up. Brown dwarfs and rogue planets together cannot explain all of dark matter, but they do contribute, and we didn't know how much until Webb began counting them. The invisible census is underway. Every observation adds new entries, new objects that were always there, lurking in the darkness, waiting to be found. Some of Webb's discoveries are not just surprising. They are reminders that the universe operates on scales and timelines that dwarf human comprehension. Carbon, for example, is everywhere in the universe. It forms in the cores of dying stars and is scattered across space in supernova explosions. It is the backbone of organic chemistry, the foundation of life as we know it. Under the right conditions, it transforms into something extraordinary: diamonds. Webb has found evidence that diamond formation may be happening inside alien worlds, not as rare gemstones buried in rock, but as entire layers of crystallized carbon deep within planetary interiors. The lemon-shaped planet orbiting a pulsar, discovered in 2025, offers the clearest example. Its atmosphere is dominated by carbon, with soot-like clouds drifting through its helium-rich skies. Beneath that atmosphere, pressures build to levels that would crush any material on Earth. Under such pressures, carbon does not remain as soot, it crystallizes. Atoms lock into the rigid lattice structure of diamond, layer upon layer, building up over billions of years. Scientists cannot see inside this planet directly, but they can model what happens when carbon-rich atmospheres overlay dense interiors. The physics is well understood. At sufficient pressure and temperature, diamond formation is inevitable. The planet may have a diamond core. This is not confirmed in the sense of direct observation, but it is consistent with everything Webb measured: the atmospheric composition, the extreme pressures implied by the planet's proximity to its pulsar host, and the spectral signatures of carbon in various forms. And this planet is not unique. Theoretical models suggest that diamond-rich interiors could exist in many worlds throughout the galaxy. Gas giants with enough carbon in their atmospheres, super-Earths with extreme internal pressures, and rogue planets that formed from carbon-rich material in the first place. The implications extend beyond geology. Diamonds conduct heat efficiently, so a diamond-rich layer inside a planet would affect how heat flows from core to surface. It would influence volcanic activity, atmospheric evolution, and potentially the conditions for habitability on any moons orbiting such a world. We are only beginning to understand the exotic chemistry that governs alien planets. Webb has revealed that the universe is not composed of the familiar materials we see on Earth. It is filled with extremes, pressures that compress atoms into new configurations, temperatures that melt rock and vaporize metal, environments where the ordinary becomes extraordinary. Carbon is just one example. Other elements may behave in equally surprising ways under alien conditions, metallic hydrogen in the cores of gas giants, superionic water ice in the mantles of ice giants, and exotic alloys formed under pressures we cannot replicate in any laboratory. Webb is a window into these extreme environments. It cannot visit these worlds or drill into their cores, but it can measure their atmospheres, infer their compositions, and model what lies beneath. And what lies beneath is stranger than we ever imagined. But the universe is not just a place of strangeness and extremes. It is also a stage for beauty, tragedy, and the slow, inevitable march of cosmic time. 13 billion years ago, a galaxy died. Not in a spectacular explosion, or a dramatic collision, but simply by running out of the raw material needed to make new stars. The galaxy went quiet. Its existing stars continued to shine, but no new ones were born to replace them. Webb found this cosmic relic in 2024, a dead galaxy from an era when the universe itself was only about 700 million years old, making it the youngest galactic graveyard ever discovered. This shouldn't have happened so quickly. Most galaxies form stars for billions of years. The Milky Way, for example, is still producing new stars more than 4 billion years after it formed. Star formation is the heartbeat of a galaxy. When it stops, the galaxy is, in a cosmic sense, dead. But this ancient galaxy had already ceased star formation when the universe was just a fraction of its current age. Astronomers call these objects quiescent galaxies. They are not rare in the modern universe. Many elliptical galaxies show little ongoing star formation, but finding one so early challenges our models of how galaxies evolve. What could have shut down star formation so efficiently? The most likely suspect is the supermassive black hole at the galaxy's center. As black holes feed, they release enormous amounts of energy. Jets of radiation and superheated gas blast outward, heating and expelling the cold gas that would otherwise collapse into new stars. This process, known as feedback, can sterilize a galaxy in a remarkably short time. Webb's observations support this idea. The dead galaxy shows signs of having hosted an active black hole in its past. The black hole may have consumed so much material so quickly that it destroyed the very conditions needed for continued star formation. In a sense, the galaxy choked on its own appetite. This discovery, published in Nature in 2024, reveals something profound about the relationship between black holes and their host galaxies. They do not simply coexist. They shape each other's destinies. Black holes can nurture galaxies by stirring up gas and triggering star formation, or they can destroy them by blowing that gas away. The balance between creation and destruction plays out across cosmic history. Some galaxies thrive, others die young. Webb is cataloging these outcomes, mapping the cosmic graveyard that stretches across billions of light years, and in doing so, it is teaching us about the fate of our own galaxy. The Milky Way has a supermassive black hole at its center. It is relatively quiet now, but it has fed before and will feed again. In about 4 billion years, our galaxy will collide with Andromeda, the nearest large spiral galaxy. The two will merge, their stars scattering into new orbits, and their central black holes will eventually combine into a single, even more massive monster. This is not speculation. It is confirmed by decades of observations. The motion of Andromeda relative to our galaxy has been measured with extraordinary precision. The collision is inevitable. Webb has shown us what such galactic collisions look like in real time. Across the distant universe, the telescope has captured galaxies in various stages of merger, spirals distorted into chaotic shapes, streams of stars torn from their parent systems, and bursts of star formation triggered by the compression of gas clouds. At the centers, Black holes draw closer, preparing for their own union. These images are previews of our future. The merger will not destroy Earth. Stars are separated by such vast distances that direct collisions are extremely rare. Our planet will likely survive, flung into a new orbit around the merged galactic core. The night sky will change, constellations will dissolve, but the world itself will endure. What Webb has revealed, however, is that mergers are not gentle. The gravitational chaos triggers waves of star formation. Gas clouds collapse under the stress of tidal forces. Supernova rates spike as massive, short-lived stars are born and die in rapid succession. Radiation bathes entire regions of space, and the central black holes do not merge quietly. As they spiral together, they emit gravitational waves that ripple through space-time. The final coalescence releases more energy than all the stars in both galaxies combined, a silent thunderclap echoing across the universe. Future gravitational wave detectors will be able to sense mergers like the one that awaits us, but that technology is still years or decades away. For now, we can only observe the aftermath of distant collisions and imagine what our descendants will witness. Webb has also shown that galactic mergers enrich the cosmos with heavy elements. The star formation triggered by collisions produces massive stars that live fast and die young. Their supernova scatter iron, gold, uranium, and all the other elements heavier than hydrogen and helium. The collision with Andromeda will enrich the merged galaxy with new material. Future generations of stars will form from this enriched gas, and future planets will incorporate these elements into their crusts and cores. In a very real sense, the collision will be an act of creation, destruction, and rebirth intertwined. Webb cannot see the future, but it can show us the past. In the past, it has found countless examples of galaxies transforming through merger, evolving, and changing. The universe is not static, it is a machine of constant renewal, and our place within it is smaller than we ever imagined. 40 light-years is nothing in cosmic terms, a rounding error on the scale of the galaxy. Yet within that tiny radius, Webb has found 7 Earth-sized planets around a single star. These worlds once seemed like promising candidates for life, but one by one, they have been ruled out. TRAPPIST-1b is scorched and airless. TRAPPIST-1t is the same. TRAPPIST-1d shows no sign of an Earth-like atmosphere. The outer planets are still under investigation, but the pattern is troubling. The closest potentially habitable worlds we know of are being eliminated one after another. And this is just one system. The nearest star system, Alpha Centauri, may harbor a giant planet, but giants are not hospitable to life as we know it. Any moons they might possess remain hypothetical. The nearest confirmed exoplanet orbiting a single star like our own is Barnard's star B. About 6 light-years away. Its mass and orbit suggest a frozen world far outside the habitable zone. Webb has found thousands of exoplanets across the galaxy, but the ones close enough to study in detail are proving hostile, and the ones that might be habitable are too far away for current technology to examine thoroughly. The silence is deafening. For over 60 years, we have searched for signals from other civilizations, radio telescopes scanning the skies for artificial transmissions, optical surveys looking for laser pulses. So far, nothing. Not a single confirmed detection of intelligent life. Some scientists argue that our search for extraterrestrial intelligence has barely scratched the surface. The galaxy is vast, and our instruments are limited. We have only sampled a tiny fraction of the possible places where life might exist. Others suggest that the silence we encounter could have a darker explanation. Perhaps intelligent life is exceedingly rare, or maybe civilizations tend to self-destruct before they can reach out across the stars. It's also possible that the conditions required for complex biology are so specific that Earth is a rare exception. The James Webb Space Telescope cannot answer these questions directly. It was not designed to search for life itself. But every world it studies adds a new piece to the puzzle. Each atmosphere it analyzes either supports or challenges the idea that habitable conditions are common in the universe. So far, the evidence is mixed. Rocky planets are abundant, this much is certain. But rocky planets with stable atmospheres in the habitable zones of quiet stars seem to be rare. The universe is full of worlds, but most of them appear to be lifeless. This doesn't mean we are alone, only that the search is more difficult than we hoped. If life does exist elsewhere, it may be separated from us by distances we cannot cross, by timescales we cannot comprehend, or by gulfs of empty space that make communication impossible. We are very small, and the universe is unimaginably large, but we keep looking, hoping and pointing our telescopes into the darkness, waiting for an answer. Since its launch, the James Webb Space Telescope has rewritten textbooks, shattered old assumptions, and revealed a universe more complex and mysterious than anyone expected. It has shown us black holes that grew too quickly, galaxies that formed too early, planets that defy the rules, and atmospheres that shouldn't exist. It has found rogue worlds building their own systems in the darkness between stars. Through all these discoveries, one message is clear: we are smaller and less central than we ever imagined. The universe does not revolve around Earth. It is indifferent to human timescales and concerns, operating on principles that stretch across billions of years and distances so vast that even light struggles to cross them. Webb has given us a new perspective on our cosmic neighborhood. Alpha Centauri, just 4 light-years away, may host a giant planet we never knew existed. Asteroids pass through our orbital space, sometimes with little warning. The stars we see at night are often violent and unstable, surrounded by radiation that would sterilize any world too close. Yet, amid all this, Webb has also shown us beauty: nebulae glowing with the light of newborn stars, galaxies spiraling through the void, and planets forming inside rings of dust, following the same processes that built our own world billions of years ago. Creation and destruction, life and death, the same cycles repeat across the cosmos on scales that humble the imagination. And somewhere in that vastness, we exist, a small, rocky planet orbiting an ordinary star in an unremarkable spiral galaxy. One world among trillions, one species among however many might exist, scattered across the observable universe. Webb cannot tell us if we are alone, but it can help us understand what to look for: atmospheres with the right chemistry, planets in the right orbits, and stars stable enough to allow life to arise. The search continues. Every observation adds another piece to the puzzle, refining our understanding of what is possible and what is not. The universe is not hostile, just indifferent. Yet in that indifference there is room for hope. Life arose here so it could arise elsewhere. The ingredients are scattered across every galaxy Webb has observed. Whether intelligence ever joins us in the silence remains unknown. But we are no longer guessing in the dark. We are looking, measuring, and learning. The James Webb Space Telescope is more than a machine. It is a mirror, reflecting back to us our own smallness and our own potential, showing us where we came from and hinting at where we might go. The journey is only beginning. If you have followed this far, you are part of that journey. Every question you ask, Every moment you spend looking up at the night sky connects you to the same curiosity that built this telescope and sent it to the stars. We are the universe becoming aware of itself, and Webb is helping us see. But the surprises are not over. Black holes, for example, are supposed to stay anchored at the centers of galaxies, held in place by the gravity of billions of stars. They are like cosmic drains, pulling matter inward and growing slowly over eons. They do not move except when they do. In late 2025, Webb confirmed something that had been suspected for years. A supermassive black hole hurtling through space at over 2 million miles per hour. Not drifting, not wobbling, but running. The object was first noticed by the Hubble Space Telescope as a strange streak of light trailing from a distant galaxy. At first, researchers thought it might be a cosmic ray hit on the detector, an artifact, or a glitch. But the streak persisted in follow-up observations. When Webb turned its infrared eyes toward the source, the truth became clear. A supermassive black hole had been ejected from its home galaxy, kicked out by gravitational forces so violent that they overcame the pull of hundreds of billions of stars. This phenomenon is called a three-body interaction. When galaxies merge, their central black holes spiral toward each other. If a third black hole enters the system, the gravitational dynamics can become chaotic. One of the three can be flung outward at tremendous speed, while the other two merge. That's what happened here, confirmed by spectroscopic analysis that matched the velocity of the runaway to predictions from computer simulations. But the streak of light trailing behind the black hole is not just debris, it is stars. New stars forming in the wake of the monster as it plows through intergalactic gas. The black hole compresses the gas as it passes, triggering collapse and igniting star formation in a trail stretching over 200,000 light-years. It's a cosmic contrail, marking a path of destruction and creation. Nothing like this has ever been observed before. The implications are unsettling. If supermassive black holes can be ejected from galaxies, then the universe contains wandering monsters we have never accounted for. Black holes with no galaxies to call home, no stable orbits, and no predictable paths. How many are out there? We do not know. Detecting a runaway black hole requires catching it in the act of interacting with surrounding material. If it passes through empty space, it leaves no trace. The one Webb found was discovered by chance, a lucky alignment, a fortunate observation. There could be thousands more, maybe millions, silently threading through the cosmic web at unimaginable speeds. It's a sobering thought. Our own galaxy will one day merge with Andromeda, and both contain supermassive black holes at their centers. If the merger plays out in just the wrong way, one of those black holes could be flung out, becoming a cosmic wanderer. The universe is more unpredictable, and perhaps more dangerous, than we once believed. But not all threats are distant or theoretical. Sometimes, the most surprising discoveries are right in our own solar system, in places we thought we understood. Take Titan, Saturn's largest moon. It's long been known as one of the strangest worlds nearby, with a thick, hazy atmosphere denser than Earth's, and lakes and rivers not of water, but of liquid methane and ethane. For years, scientists have speculated about the weather on Titan. But in 2024, Webb provided the clearest evidence yet of active meteorology. The telescope captured images of methane clouds forming and dissipating in Titan's northern hemisphere, confirming that this alien world experiences storms and rainfall, just like Earth, but with a chemistry utterly foreign to us. These methane clouds rise, cool, and condense, eventually raining hydrocarbons onto the surface below. The cycle feeds rivers that carve channels into the frozen landscape and fill vast lakes. Webb's observations, combined with data from ground-based telescopes, allowed scientists to track the evolution of these clouds over hours, revealing a dynamic, living atmosphere. The implications are profound. If complex weather systems can operate on a frozen moon, nearly 1 billion miles from the Sun, then similar processes might occur on countless worlds throughout the galaxy. Exomoons orbiting giant planets, rogue planets with thick atmospheres, or even distant worlds with internal heat sources, all could have weather, driven by chemistry we are only beginning to understand. Titan is also a laboratory for prebiotic chemistry. The organic molecules raining from its skies are the same building blocks that may have led to life on early Earth. While Titan is far too cold for liquid water, and thus for life as we know it, the chemistry is tantalizing. Webb will continue to monitor Titan as its seasons change. A single Titan year lasts 29 Earth years, and the northern summer is just beginning. The storms may intensify, the lakes may swell, and we will be watching. Closer to home, Jupiter, our solar system's largest planet, has also revealed new secrets under Webb's gaze. Jupiter is a world of extremes: the fastest rotation, the strongest magnetic field, and the most powerful auroras. In 2024, Webb captured the planet's auroras in unprecedented detail, showing them not as static glows but as dynamic, flickering displays that change from minute to minute. These auroras are fueled not just by the solar wind, but by material from Io, Jupiter's volcanic moon, which spews sulfur and other elements into space. This material is swept up by Jupiter's magnetic field and funneled toward the poles, creating auroras that make Earth's northern lights look tame by comparison. Webb's infrared vision revealed temperature variations and chemical changes in the auroral zones, as well as unexpected features above the famous Great Red Spot. Layers of haze and unusual molecules suggest that the storm extends higher into the atmosphere than previously thought. Jupiter is not a static world. Its storms shift, merge, and evolve, and its auroras pulse with rhythms we are only beginning to decipher. Even the most familiar planets can surprise us. But some of Webb's most astonishing discoveries have come from objects passing through our solar system from the depths of interstellar space. In late 2024, astronomers detected a comet designated 3I Atlas that was not born in our solar system. It was only the third confirmed interstellar visitor ever found. Webb observed the comet as it made its closest approach in 2025, revealing a coma, jets, and a faint tail, just like comets from our own system. But its chemical makeup was different, with ratios of elements and compounds that pointed to an origin around a distant star, in a planetary system with conditions unlike our own. This interstellar comet is a fragment of another world, ejected into the void and wandering for aeons, before passing through our neighborhood. Its brief visit taught us that interstellar objects are not rare. We simply lacked the tools to detect them until recently. The galaxy is full of debris, remnants of planetary formation, drifting between the stars. Some of this material may carry complex organic molecules, seeding new worlds wherever it lands. Webb cannot track every interstellar visitor, but each one it studies tells a story about a solar system we will never see. Beyond our solar system, Webb has begun to map the vast structure of the universe itself. Galaxies are not scattered randomly. They are connected by immense filaments of gas and dark matter, forming a cosmic web that stretches across hundreds of millions of light years. Webb has imaged portions of this web directly, using the light from distant quasars to trace the distribution of hydrogen gas between galaxies. The data revealed filaments exactly where theory predicted, but also showed that the distribution is clumpier and more complex than simulations suggested. This matters because the cosmic web controls how galaxies grow, feeding them with gas and shaping their evolution. And hidden within this web is the greatest mystery of all: dark matter. It makes up about 85% of all matter in the universe. Yet it cannot be seen or touched. Webb cannot detect dark matter directly, but it can observe its effects through gravitational lensing, when the gravity of a massive object bends the light from something even farther away. In every case, the amount of mass required to produce the observed lensing far exceeds what we can see. The dark matter is there, shaping the universe, but its true nature remains elusive. Webb's observations have confirmed that dark matter behaves as expected on large scales, but the details are still frustratingly out of reach. Is it made of undiscovered particles, primordial black holes, or something even stranger? The answer remains one of the biggest open questions in science. Every new observation adds a piece to the puzzle, but the universe keeps its secrets well. Yet, amid all these mysteries, Webb has also shown us the places where new stars and planets are being born. The telescope's infrared eyes can peer into the dense clouds of gas and dust, where stars ignite and planetary systems take shape. In regions like the Carina Nebula and the Orion Nebula, Webb has revealed hundreds of newborn stars, jets of material shooting from young stellar objects, and disks of dust where planets are beginning to form. The process is more efficient than models predicted, with more mass turning into stars and planets than previously thought. Creation is happening right now, all across the galaxy. And as Webb continues its mission, it will keep pushing the boundaries of what we know. It will find new worlds, new mysteries, and perhaps, one day, the first hints of life beyond Earth. For now, it reminds us that we are part of a vast, ancient, and ever-changing universe. A universe that is stranger, more beautiful, and more surprising than we ever imagined.